Hello everyone, welcome to Zeref Game Dev. In this video, I'll share how I made my code 1000 times faster by utilizing data structures such as linked lists, queues, hash sets, and caching. I'll take you through my journey from slow and inefficient program to a lightning fast one. By the end of this video, you'll have a solid understanding of how data structures can help your code perform better. First, let's define our problem statement. We need to generate levels for our Connect game. While I don't have a concrete plan yet, we can start with the colors assigned at the start to generate the levels. So let's take a look at our random spawning script. To start off, I created a 2D grid and set all of its values to -1. To ensure that no two neighboring cells have the same color, I generated two random positions that must be distinct and both should not be neighbors. The code to achieve this is relatively straightforward. Let's see how that looks in Unity. As you can see, we can generate multiple levels with different starting positions. It's not the correct approach, but we can expand from here. The previous approach was found to be incorrect. Instead, we need to fill the grid with valid moves starting with coloring one of the cells. To accomplish this, we will store our grid in a grid data class, which has two constructors, one for creating the starting grid and the other for passing moves from another grid. It also contains a few functions that will be useful. Let's see how we are going to solve this. All moves will be stored in a list. We'll fill the list with starting moves. Whenever we expand a move, we'll mark it as solved. During each loop, we will expand and insert into our current list. There will be two types of moves. One where we expand our current flow and another where we create a new flow. The process will continue until all moves are solved. Let's take a look at how this approach works for our 3x3 grid. It shows us all the possible moves, but it requires around 10,000 checks. Unfortunately, our current code won't work for the 4x4 grid because the number of required checks will exceed 100 billion. We'll need to further optimize our script to handle the 4x4 level. Let's discuss optimization. Accessing an element from an array is a direct process and takes only one step with O of 1 complexity. However, searching for an element in an array takes O of n complexity, where n is the size of the array. We can improve this by using dictionaries, where each element is assigned a hash code and then stored. Instead of searching the entire dictionary, we can just check if the element is present at the index, resulting in O of 1 complexity. However, our problem has an exponential complexity where the number of digits increase with the total number of cells. For example, a 3x3 grid has 9 cells and a 4x4 grid has 16 cells. The number of digits doubles with double the amount of cells, resulting in the 100 million checks mentioned earlier. Let's discuss how using a linked list can improve our code. When it comes to inserting an element in a list, it can affect the entire list, which take off and time. Adding elements is also expensive as there may not be enough space leading to resize. To tackle this, we can use linked lists. In linked lists, data is stored as nodes, each node containing data and a reference to the next node. When we want to insert or add, we can directly modify the connections, which takes off one time instead of n time required in lists. Using linked lists instead of lists will help optimize each step and eliminate the additional work of modifying every element in the list. Let's take a look at the implementation of a linked list in the script. I've created a grid list class that contains a reference to the next node and the grid data. Instead of using a list, we are using our grid list. We'll add the start moves, and to solve all the moves, we will start by expanding each of the moves and then move on to the next. This will ensure that previous nodes will always be solved and the neighbors will be together. When no moves are possible, the loop will end. As we are using a depth first approach, we can solve one move at a time instead of using a breadth first search where we solve moves of different sizes at a time. We have reduced the time for insertion and adding tasks, but we need to further reduce our checks. We can do this by identifying where some moves may be similar. For example, at the start, the corner moves are all going to be the same, as well as the reflections. This means we would have 8 copies of each move if we use our previous method. To avoid this redundancy, we can store each move in a set and compare if it is already present. This caching method saves us the time it takes to expand similar moves since we would have already calculated them. We reduced our moves that had similar directions, and now we can further reduce moves that have similar colors. Suppose two grids are similar in the sense that all empty positions and flows are the same, but the assigned colors are different. We need to create custom comparison and equality functions to check the equality of our grids. With 5 colors, there are 120 different color combinations available, which will further reduce our moves. Let's take a look at how we have implemented this in our code. To obtain similar grids that are reflections and rotations, a function was created in the grid data class that returns a list of such grids. The equality comparer was then implemented to check if two grids are equal, which involves ensuring that both grids have the same empty positions and that the corresponding numbers are the same. A unique hash code was generated for all similar grids by checking if they have a neighbor in the four directions, thereby reducing the dependency on color and implementing color similarity. Starting moves are initialized and added only if they were not present in the grid set. For adding new ones, the same approach was taken, checking if the move was already present before adding it. The resulting code works perfectly fine and enables solving of the 3x3 grid with reduced checks. Let's visualize our 3x3 grid. We can set the speed to our preference since it only has 300 checks. Despite the code's inefficiency, we can solve our 4x4 grid with reduced checks and view the moves. However, for larger grids, we need to further reduce the time taken for each step. I've created an algorithm for solving the 4x4 grid, which is at least 100 times more efficient than the previous one. However, it is still slow for larger grids, so I need to determine which functions are taking the most time. To do this, I used Unity Profiler and turned on advanced debugging. Previously, I mentioned that I use vector2 for calculations. After using the profiler, I discovered that the dictionaries vector2 and my custom hash code function were the tasks that took the maximum percentage of work. Therefore, I replaced every occurrence of vector2 with my custom struct and replaced dictionaries with a 2D array, which should improve efficiency. The code optimization involved changing data types from a vector2 to a custom struct and replacing dictionaries with a 2D array for efficiency. The new method was much faster than the previous one. The 3x3 grid was significantly faster, and the speed for the 4x4 grid increased from 10,000 to 16,000, making it much more efficient. Before the optimization, the 4x4 grid would have taken over 100 billion checks, and with the slow speed, viewing the solutions would have been impossible. The code still works for higher grids with reduced speed. To further reduce the number of moves needed, I implemented a branch reduction script. I added a new function that returns the neighbors list and the empty positions list. First, I calculated the number of empty cells surrounding each empty cell and categorized them into 0° neighbors, 1° neighbors, and so on. If there are two or more 0° neighbors or any 0° empty positions, the move is invalid. If there are any 1° empty positions, I prioritize those. Otherwise, I include all the valid moves. It's a simple filtering of unnecessary moves. This improvement significantly sped up the algorithm. Let's examine the reduction in checks for the 3x3 grid. Previously, there were 300 checks, but now it has been reduced to 150. The total number of correct solutions for the 3x3 grid remained unchanged at 3. Moving on to the 4x4 grid, the number of checks has reduced by almost 10 times from 170k. This confirms the goal of making the script 1000 times faster. Not only is it 1000 times faster for larger grids, but the number of checks is also significantly reduced. For example, a 100x100 grid, it may be reduced by billions of times. However, the script is not perfect yet. Let's take a look at the 5x5 grid, which is running quite fast without any problems. As we increase the grid size, we may encounter more issues. To visualize the problem, I need to select a random move from possible moves. Previously, I was using a linked list, but now I have improved my coding skills and learned about trees, which is why the previous script was called branch reduction. I have converted my linked list to trees for traversal, and when there are no possible moves, I will go to the previous node. If any moves are possible, I will go to the next random node. The implementation of the move solving script now looks much more organized than before. I created a new function that returns the minimum size region of empty cells for selecting empty positions. To accomplish this, I used queues, as it was the simplest method I learned. Only empty positions from the minimum region will be selected. Let's review the performance of my moves. The total checks for the 3x3 grid were reduced to 111, And for the 4x4 grid, it went from 20k to 15k, which is not a significant improvement, but still better than the previous version. As I switched to using graphs for node traversal, the required space has decreased, and I am getting random grids for each level, which is an improvement over the previous method, where the same grid was repeating. This will help me debug more efficiently. However, there may still be more problems that need to be addressed. Check out my Udemy course on creating a puzzle game in Unity, which covers advanced programming concepts. The entire series is available on YouTube in the provided playlist. If the course helped you improve your programming and data structure skills, consider purchasing it for only $50 to support my work and help me create more free content on YouTube. Let's examine the final obstacle, the bubbles. The bubbles are a hindrance to the script as they cause the program to run unnecessary checks. The longer a bubble exists in the flow, the more checks are performed. I have minimized this issue by selecting the smallest possible area for the flow extension. I have already implemented bubble detection for a 0-degree neighbor. I need to detect bubbles for groups of cells now. Solving 1 and 2 cell bubbles is impossible, but a 3 cell bubble is solvable. For larger bubbles, I need to check if a valid solution exists. If not, I will discard the current move by setting all its children to null. Since I already created the script to solve flows, I can set any other region to be a block and solve the given region. For cells up to size 9, I can solve them in around 100 tries. If there is a valid solution, it will be solved faster. I also need to implement this when extending the flow as there may be multiple regions created. I just need to solve the unreachable ones and check if all of them are solvable. The time taken to reach a valid solution has been reduced to a linear amount of the number of cells, further reducing the worst case scenario. If an unsolvable part is encountered, it will take more than 5000 checks, but the max level size is only 100 cells, which is manageable. The 7x7 level took around 200 checks to generate, and if it takes more, it can be restarted. The hash set was removed as it was unnecessary, and the process repeats with different random sets of moves. The final level generator script combines all the elements, generating all the levels for the game. Let's see all the levels being generated. I will now demonstrate the 7x7 version of the level generator, but the previous versions are similar. This concludes this video. If you enjoyed it, please give it a thumbs up. Thank you for watching, and I will see you in my next video.